or interpretable latent factors. For example, here is an example, we map the avatar to a low-dimensional latent space. So here there are some elements in the latent representation corresponds to high-level concepts like here, eyes, nose, and mouth. So this can help us better understand and explain the deep neural networks. For example, if I can choose the factor of here, it can change the style of the generated image. This is example that we can imagine, we map the image into a latent space. So each latent representation corresponds to a very meaningful, attributes like smile, gender, and beard. So some applications of deep representation learning include deepfake. For example, we can generate some, very fake or real, video, like the ground truth video. And also like some very interesting research by Google, like image generation. So here you can see the astronaut is riding horse on the moon. And also, yeah, this is also a very famous model developed by OpenAI this year. For example, you input a sentence, you can generate, different paintings based on this sentence. So if you are interested, you can click this website. You can type any sentence. You can generate, the paintings. Okay. For example, here, yeah, if we input an armchair in the shape of avocado, then it can generate, chair like avocado. Okay. So these are some applications of deep representation learning. This is for in painting. My second research topic is physics-guided machine learning. So compared to the traditional purely data-driven machine learning model, so we try to incorporate the physical knowledge into the deep neural network. So example, if you want to predict the car trajectory, we can incorporate the Newton's second law in the deep neural network. So we are going to, submit a paper to the Nature Communication at the end of this month. So yeah, the application of physics-guided machine learning like climate change, the drone trajectory prediction, the dark matter simulation. Yeah, so a lot of applications. The next topic I'd like to introduce is on-device federated learning. So federated learning is an emerging distribution machine learning paradigm, which collaborates trains the local model without sending the data to a central server. So it can protect, users' data privacy. For example, you have, tens of thousands mobile devices. You can train your model in your local devices. You only send the parameters of deep neural network to the server instead of data. So this is also very hot in the Google research because it can protect users' data privacy. Yeah, so here we try to use knowledge distillation for federated learning. So 2 undergrad students at William Mary who work with me just submitted one paper to a top tier AI conference, iClear. And also I'm, actively working with some, top schools in the US and around the world, like Georgia Tech, UCLA, UIUC, and also I'm collaborating with some industry labs like Amazon Research, Google Research, Alibaba, and AT&T Research Lab. Yeah, so thank you very much.
All right. Just a quick reminder for the speakers, we have a clicker here. So if you want to use it, feel free to do so for switching the slides. Anyway, my name is Oscar Chaparro. I'm an assistant professor here at the department. I started 3 years ago. And well, I lead the Software Evolution and Analysis Lab. These are my students, Yang and Addition. And well, we focus on making life easier for developers. We want them to be productive and build high quality software, right? And we do that by applying different methods We apply a lot of natural language processing, machine learning, information retrieval, program analysis, and also we conduct multiple studies with users by analyzing software artifacts and so on. Our main research area is software maintenance and evolution, trying to help developers change software, large software systems, help them understand software systems, and help them change software systems. So our more specific areas of research are software comprehension, trying to software documentation, which is basically giving the right information for developers at the right time, hopefully automatically. We want to increase the productivity of developers by, proposing methodologies, tools, techniques that can help them in different tasks of the software development process. And of course, we want to measure and be able to improve quality as much as we can. And one of the specific lines of research we work on is on managing software bugs or failures, right? And they are very common when you use software, right? And also when we test software as well. Developers test software to find bugs, essentially. And usually these bugs are reported via issues, like in the GitHub issue tracker or Jira, right? But also they can be reported using graphical means, right? For example, a video, images, or a combination of these things, right? These are the input for developers to basically address the bugs in the software, right? And in that process, when they get the bug reports, well, there is a series of steps that they need to do. They need to understand the bug. They need to see if there are other bugs that are related to the bug. They need to find the bug in the code, right, automatically. Also to fix the bug, right? So this is called bug report management. It's all the steps to manage these bug reports. And in our lab, what we have done is to basically make this process automated. And we have proposed techniques and tools to basically automate some of these steps. And we have published in top software engineering venues, as we can see here. And actually the community have recognized our work with some awards. We have earned best paper awards in multiple conferences. And well, my student is going to give a talk. It's going to be a talk by the poster session about this work, about developing a chatbot that interactively helps users and developers to report bugs. And well, I don't want to give you more information, but essentially we use a series of techniques, dynamic program analysis. We use natural language processing. We use human-computer interaction methodologies to basically help users in that regard. So if you are interested, please stop by the poster session. My student can give you more information. Some more projects involve supply, are about software supply chain. Essentially, people build software with packages, right? Open source packages, multiple open source packages, right? From different ecosystems. And well, there may be vulnerabilities in those systems, or they need to comply with licensing, right? So the idea is to develop techniques to help developers and users to deal with this problem. So dependency management, license compliance, regulatory compliance, and also vulnerability management. So this is another line of work that we're working on. And another one, which is fairly new, is trying to help developers make the right decisions when they change the software, right? And our approach is basically to reuse the decisions that people have done in the past. And by mining software repositories and having automated tools, the idea is to help them to have recommendations for developers to make the right decision when changing software. For example, changing a class in this way, or introducing a design pattern here and there, right? Or use the right library. Okay, as I said before, so our research approach is empirical. We conduct studies to analyze software artifacts like code, bug reports, and more information. We conduct studies to understand the processes and tools that developers use when building software. And we propose automated techniques to help them produce better software. we have funding for you guys if you're interested. That means that the community has recognized our research in our lab. So there are 2 grants and more to come to fund our research. And well, of course, our network of collaborators help us with that, right, as well. So our lab works with colleagues from around the world and here from the US, and also from universities and from companies. And that's it. Thank you very much for your attention. Happy to talk to you during the breaks. Next is Stephen.
I don't know why we're losing in-room audio, but please keep using the microphone for Zoom.
Okay. Hi, I'm Stephen Herwig. I'm new faculty here. It's wonderful to see you all here today. So over the past decade, there's been this tremendous shift in how companies and other institutions run their major software applications. So rather than running them on-premise on hardware that the company actually owns, instead, they run them in the cloud. What's the cloud? Well, the cloud is a set of machines owned by someone else who we call the cloud provider. And companies willingly outsource their applications hosting to the cloud because it's cheaper and more flexible than managing the hardware themselves. Now, despite these benefits, there's a major shortcoming, and that's that the companies have to trust the cloud provider, as well as the low-level software that the provider is using to actually run their application. Why is that? Well, if the provider is malicious, then they can easily access and alter the company's software as well as its sensitive data. So this leads us to the question, well, how can we run our applications in the cloud without having to trust the cloud provider or its software? Unfortunately, in the last few years, all of the major chip designers, so Intel, AMD, and ARM, have come up with a similar solution to this called a Hardware Trusted Execution Environment, or T for short. And so the basic idea behind the T is that the CPU is trusted, and it's been modified in 2 ways. The first is to be resistant to physical attacks. And the second is to run software in such a way that shields it from the rest of the system, which is considered untrusted. And the way it shields it from the system is that the application and its data are encrypted while in memory, and they're decrypted by the CPU whenever it fetches that memory. And the term that's often used for an application running in a T is an enclave. So problem solved, right? To safely run our applications in the cloud, simply run them in an enclave. Unfortunately, it's not quite that simple. So in the remainder of my talk, I want to give a flavor of some of the interesting research problems in this area, as well as my approach to trying to solve them. Okay, so the first problem is how to make enclaves easier to use. So just as other parts of the system can't look in to the enclave, the trusted hardware restricts how much the enclave can look out and interact with the untrusted world. So if our application wants to write to a file or send data over the network or allocate some memory, the trusted hardware prevents that, it disallows it. So this actually means that in order to run our application in an enclave, we have to modify it, which in many cases is prohibitively expensive. So the second problem is performance. And there are 2 major bottlenecks. The first is memory. And that's because since the memory is private and encrypted, the other parts of the system, so the hardware and either the OS or the hypervisor, can't manage it as effectively as it can normal memory. And the second bottleneck is I/O. And that's because, again, for security purposes, the trusted hardware prevents the enclave application from issuing direct I/O operations. So my approach to solving both the ease of use and the performance problems has been to actually create a small operating system that runs inside of the enclave with the application. And since the application interacts with this small OS, we can actually run unmodified software. And since the small OS is sort of handling some of the resource management of the application, as well as preventing these costly context switching to the untrusted world, it also helps to improve performance. Lastly, given that these trusted execution environments are now somewhat commonplace, another interesting question is, well, what new kinds of applications can we write that maybe weren't possible just a few years ago? And so I'll briefly mention that my colleagues and I have investigated incorporating enclaves into the Tor anonymity network, both to increase performance as well as a user's anonymity. Okay, so today I've described the cloud's major privacy challenge. I've described how the major chip designers have responded to that challenge through the design of these trusted execution environments. And then the software, the research that I'm working on, which leverages that trusted hardware in order to seamlessly run applications in the cloud without having to trust the cloud provider. You can find out more about this research at the link here, and I look forward to meeting you all throughout the day.
Hello, everyone. I am an assistant professor here. I will briefly introduce my research about democratizing the big application deployment. So the big applications are here to trying to solve a lot of big problems. For example, we have this scientific simulation, which are trying to emulating some physical or theoretical systems. And we also have this very large machine learning and artificial intelligence application. For example, we have this machine translation software, or we have this personalized feed, which trying to steal all your time and energy and money. And also we have this very large scale in memory databases, which are used, which is the foundation to the your book ticket, to book your tickets and doing a lot of things. So have you ever thought about how those applications has been deployed in the modern hardware? Let's see the process of how this big application has been produced. The data scientists or software developer, they are getting a lot of data and they are knowing their goals. They're trying to figure out some solutions to do the computation and get their data. But that's not the end. We need to figure out a way to deploy this application with modern hardware. In terms of the hardware, we have different kind of computer resources. For example, we have the CPU and we have all kinds of accelerators such as the GPU, TPU, and FPGA. In terms of storing those data, we have different memory devices such as DRAM, the high bandwidth memory, the persistent memory, and we can even store all those large data into the cloud. So how do we decide which devices we should use for different applications? The heterogeneity in the hardware increase the management complexity. So my work is trying to solve this problem by helping the software developer to deploy their application on the heterogeneous computing and memory systems more easily. Specifically, my work is trying to figure out the new abstraction, develops the new algorithms and the new software systems to democratizing the big application development from the data management or system standpoint. Specifically, this democratizing means that we need to both have the system efficiency and the human efficiency. In terms of the system efficiency, we want to lowest our cost to use all those hardware resources. And in terms of the human efficiency, we want the software to change their code, a software developer to change their code as less as possible. So here I would like to introduce one of my research topic here, which is about to enable billion scale machine learning model training. we have this very large machine learning model with billions of parameters, and we have these GPU clusters and trying to train the model. The model itself is too large to fit into one GPU, but how to partition the whole model into different GPU and making the GPU train it as efficient as possible. That's the problem I'm working on. And another problem I'm working on is about deploying this large-scale scientific simulation with a heterogeneous memory. Here we have this large-scale molecular dynamics, which simulate the movement of the atoms and the molecules. And we also have this heterogeneous tiered memory system, which we can see that the different memory devices have a different access latency and bandwidth. So how we can, which memory devices we should use for different molecules or atoms and making the whole simulation run as fast as enough. That's the question I'm trying to solve. So if you are interested in my research about democratizing this big application with heterogeneous computing and memory system, please reach out. Thank you.
Hello, everyone. My name is Pradeep Kumar, and I'm an assistant professor in the Department of Computer Science. So what we are working on today is, we have this wonderful deep learning system like PyTorch, TensorFlow, and that's great, if you want to reuse some of the things that has been built. But lots of time we need to actually build PyTorch's kernel, PyTorch's backhand, where some of the functionalities may not be available. And one of the right now example is sparsity. Right? Your data could be sparse, your model could be sparse. If you don't know where that is coming from, we have a particular example here that we'll talk about here. All these data that you see are actually sparse. They are not exactly image-like data where pixels have a fixed neighborhood, left, right, center, down, and all that. They have basically very variable number of neighborhoods, right? Few nodes could have millions of neighbors, while few nodes could have only 2 or 3 neighbors, right? So that's the problem today, that our data is actually sparse. And not only that, our model could be sparse. In this example, what you see today is a fully connected layer could be made sparse because that's how we want to deploy them on resource-constrained devices. If you want to deploy them in a big data center, well, Google can do that, Meta can do that. Sorry, Bill and Mary may not be able to do that because we don't have a big data center. We only have a couple of GPUs. So we definitely want them, test their accuracy, and then deploy them again on handheld devices like mobile phone or a very small sensor. So we definitely, see these kind of practical challenges today. Unfortunately, someone who is doing research on these kind of system where we need to modify the backend of PyTorch are unable to do that. Reason is, we can't really pass a sparse data and sparse kernel as a custom object in their backend. You have to think about workaround because they only allow you to pass something called a tensor data structure. Those who do research in deep learning, they know it's an array-like data structure. But once you have a custom object such as sparse data or sparse tensor, which cannot fit in exact array-like data structure, you can't do research. Well, that's the problem number one. And the second problem, we have observed that if you do those kind of work yourself, you won't be able to even run on one GPU because they have a huge memory overhead and they have huge framework overhead. So if you do decide to do research on that, unfortunately your research won't be appearing in a training time. Your training time will remain same. Why? Because we have huge framework overhead, because our data set is now smaller because of the compression that we talk about. So there are lots of problems. How you do research and how do you show your impact of research, both are basically in the same problem. Unfortunately, we don't have a solution today, and that's what we do in this work. right? So that's our motivation for the work. And the system that we have built allow you to write your backend system in very independent system, right? If you have done any Hello World application, it's so easy. I'm sure you can all do that in 10 minutes. But if I want you to write a printf statement, in a Linux operating system kernel, the first thing, how do I download and compile them, and where do I modify them? Even though it's just 10 lines of code, it might take a week or maybe a month. So what we are suggesting here is a very new, unique architecture where you should be able to write your independent code, high performance code in a very independent environment, and rest of the thing would be taken care automatically so that your kernel could be called in a training loop, and you will be able to see all of results, within, your reach. So this system is very lightweight. There are no framework overhead, and we do generate lots of code which allow your kernel to be used in actual deep training model, right? So that's the main idea. Some of the things that we have already done are with different use cases with either PyTorch or TensorFlow, so that you don't have to modify TensorFlow's backend or PyTorch's backend, right? And very simple to write, So some of the very simple thing about the architecture is we can support sparsity very easily today. We have demonstrated that with many sparse data models, at least 4 today, and we are supporting more and more for some of these sparse tensor, like fully connected layer, but simply make them sparse. So the advantage is data scientists can continue writing new layers for which kernel doesn't exist, and they can collaborate with a system researcher who can write their kernel easily. So it's a win-win situation. No, memory overhead. And let me, tell you one more thing. Because of this wonderful architecture, it's so lightweight that I'm able to use the same tool for teaching our graduate student how to do, system development and data science development together. So now within a week or two, people are able to write their kernel and also test in an end-to-end training loop, so that what we are following is an actual development environment, not asking people to write kernel in Python, because that never happens in real world. You write your kernel in C++ or CUDA in GPU. And that's the main idea behind that. And that's why, you can be trained in data science plus system both together. Okay, that is one of the work we already submitted. Now we have wonderful framework. What can we do with that? Let's do more system research. And one of the system that we are already doing is we have developed a wonderful kernel for sparse data where we are able to achieve 23 times speed up, which is, I believe, is a huge, considering there has been decades of work in this area. Okay, but why we are able to achieve that? Because the existing research has been done in isolated way in graph analytics or sparse linear algebra. Now we are understanding the requirement in a better way that tells us, that research that has been done for decades are very different than the research that we need to do today. And that is one of the reasons for the same. Okay, what we want to explore, 3D sparsity, which is very new, and we will talk about that maybe in the poster session. Okay. So thank you for your attention. And if you have any more questions, we can definitely talk outside or during the poster session.
Okay, good afternoon, everyone. I'm Gang Zhou. I'm a professor in computer science. I've been here for 15 years, so I have done a lot of work. Here, I will not present all of them. I also see some familiar faces from my undergraduate class. I'm teaching how internet works. This is not about that. This is the other side of my research. Hopefully you will enjoy it. Okay, so the big vision is ubiquitous in mobile computing. Since the mobile computing right now mostly is about mobile phones, I think I can safely put it as part of the ubiquitous computing. So there is a big vision of this research. Basically says that, okay, the technology we're enjoying right now should disappear while you're still enjoying the technology. You see, from computers to phones to watches to smart winds, whatever. So that's the vision driving my research. When you're enjoying all the functionality, but you don't have to carry your phones like soap bars and other things, less intrusive, I think this research field is done, achieved its mission. So here are some research projects I'm going to illustrate. These are the things I'm currently working on. So it's not all of my project. You can go to my website. Okay. So many of my research is funded by National Science Foundation, some by DARPA. This one is funded by NIH. It's different, National Institute of Health. Why? Because we're solving a health problem. We're working with Parkinson's disease order enrichment. So we're working with the patient. So what is the problem? The problem is that patient due to Parkinson's disease, they have a freezing gait. Basically, they want to walk, but their legs doesn't listen to them. So they're going to fall because the upper body is moving, lower part of legs not. So we need to detect that in real time and also apply a dose of another actuator called vibration. So that vibration will distract the neural system, not a neural network, but a human neural system, so that it can start to move. In order for these things to be successful, everything has to happen within about 100 milliseconds. That including detecting the freezing gait and try to also actuate the PD vibe device, another wearable device. So that said, for the freezing gait detection of the neural network we're using has to be done within 30 milliseconds. This requires a lot of science, like when you do the real-time digital signal processing, you use a time domain signal, Frank's domain signal analysis, like the typical fast-forward transfer or the constant wavelength transfer, they're too expensive for the phone computation. That will last more than 30 milliseconds. So we have to do something, even for the machine learning. If you send to cloud, you have to come back within 100 milliseconds. So that said, mostly you probably have to compute on the device, not on the wearable device like the UG motion sensor or PD vibe, but at least on the phone. So basically, we need to deliver a whole end loop, closed loop system with a human inside it. Our group, I call this Smart Health. Our group actually designed the UG motion sensor. That was done by a PhD student a few years ago on a National Science Foundation project. We also commercialize it. So this is a commercialized version. Anyway, you see when they wear on the ankle of the patients, this is how it look like. We have tested on 13 patients. They did pretty well, can do in real time and can reduce their falls. That's kind of life-saving for the patients. Another project also with health people from Richmond. So basically, Parkinson's disease patients, in addition to the freezing gait, they also have tremors. Their hands will vibrate involuntarily. So right now, they ask when the patients come to visit the doctor in their clinical environment, they will ask them to perform, for example, these 14 different activities, and from then and observe when the tremor happens, how long, and how serious it is. So those are basically need doctors' time and expertise to manually do that. We're using our IMU sensor. Again, here shows the sensor, which is actually quite small if you get rid of the case. It's like a quarter size, including battery, microcontroller, sensors, and the Bluetooth radio as well. So we designed the hardware, also designed the software. We designed the API on phone to enable app development. We also developed the app. So basically, it's from hardware, driver, algorithms, application, it's a whole ecosystem in order to solve this problem. Okay, next one. This one is working with George Mason University with their nutrition department and behavior scientist. So basically, people have diabetes, overweighted, other things. Not mostly, in many cases, due to they don't eat well, right? How do we know how well they eat? Maybe you don't know that after the smartphone, the AirPod, this earbuds is the second most popular device sold worldwide. That shows that how popular these devices are. So we want to put some function there, some science. While you're enjoying your music or whatever, you're wearing your earbud. When you're eating, crunching of the food, will generate some sounds that can go to your inside ear channel. And the earbuds, they not only have speakers, they also have microphone. There are 3 microphones on each side. So those microphone sensors could be used in real time to detect what you're eating actually. And we do have some preliminary result here shows that, for this, 10 plus some food, we get pretty good accuracy. So this is still going on. This also needs to be done in real time. And also we want to do intervention as well. Like we want to give you personalized coaches through earbud so that you can avoid eating the food probably you should not, but you want to eat. Okay, so those projects are all smart health based on sensors, based on digital signal processing, machine learning, and app intervention. Now, this one is separate. This is also sensors, but it's Internet of Things sensors. Okay, it's kind of privacy and security issue. Probably you are aware that there are smart bulbs. You can program and you can control the light conditions, the colors. It can even correspond to the music you're listening to, so that you have more vivid experience of the games or whatever the technology. However, recently there are scientists they say, okay, actually when I change the light, colors, or strengths, I can leak some sensor data. I can leak some data acquired through this kind of light side channel. So they put a RF receiver to say high light, no light, different color means bits 1, 0, or 0, 1, so that this becomes a privacy and security issue. In order to defend against this, we have a sequence of applications to design a smart plug you can plug on your wall, like many smart plug you can buy from Amazon. So we add some intelligence to say, hey, we can monitor your power consumption no matter you use battery, DC battery, or AC power as well. We can monitor, for example, like 1,000 times per second to see how your power consumption varies with time. This could be a signature of what you're doing. For IoT device, because most are single-purpose device, like for example, security cameras, you either take a picture, you detect the motion, upload a video, right? So your kind of power variance with time should be predictable, very limited. So we can use AI to detect whether you're following what you're supposed to do or you're doing something ugly to detect that. And this is the hardware we designed that can detect both AC and DC power in real time and do some machine learning. And we also distributed the different components of machine learning over the client side and the server side. Why? Because we're making this commercialized. We have a patent. We're in commercialization grant as well, because the company needs to hold some computing in the organization, not everything in cloud. So we do it in a way so that the computer in the company don't have to trust the cloud don't have to trust the computer server in the company as well. But this distributed verification can be done in real time. So that's another segment of research. I think two of these will be presented by 2 of my students as posters. So if you're interested to talk to them, that's it. Thank you.
This is the first time I'm using this. Can you hear me clearly? Okay. Thank you. Thank you for interest in research. So today I'm going to share with you just a little bit about my research projects. So it's going to be mainly related to optimal, resource allocation, online and approximation algorithms. Yeah. Okay, first, a little bit about research allocation. This is a very important problem. Usually you have high demand for some limited resources. And the main thing is you need to know how to allocate your limited resources to this demand, right? So often people use an objective function to measure the quality of the allocation, resource allocation. For example, if you have n parallel processors and n tasks, how do you allocate tasks to processors to minimize the total computing time and also minimize the communication overhead. So this is not a simple problem. Originally, I think there was mostly NP complete. But so this means that we want to focus on some other algorithms to solve this kind of hard problems. So we're going to look at first online algorithms. So what is an online algorithm? An online algorithm can only see its input piece by piece without receiving the entire input all at once. So this is called online. And in contrast, there is an offline algorithm that is also very useful. In that case, you do know the entire input sequence when you start the algorithm. So usually you get better quality of the solution. Okay. So, but also you have to look at the trade-off. For the online algorithm, you don't know the entire input information. So the output you create or the solution you create may not be the best. Okay. So sometimes you have to make a guess. Okay. And also, but for the offline algorithm, you do have the advantage of having the entire knowledge of the input. Therefore, you can actually produce a better quality solution. So in addition to online and offline algorithm and also resource allocation algorithm, I'm also interested in approximation algorithm, because a lot of the time we'll be dealing with problems that are NP complete. So this means that to solve the problem exactly, you do have to spend usually, exponential time, right? So we rely on approximation algorithms. So of course, you can easily design an approximation algorithm, but how do you convince people that the solution you get is not too bad? You want your solution to be as close to the optimal solution as possible. So this means that we need to have some kind of proof techniques to compare the quality produced by an approximation algorithm versus the quality of the optimal algorithm or the exact solution. So, so this is something in addition. I already kind of mentioned several of my interest areas, but here I want to just briefly tell you some ongoing or future work. One is, of course, right now where I'm interested in graph partition or graph algorithms because there are a lot of fun work that needs to be done there, especially nowadays. And also in my spare time, I'm interested in puzzles. And the table that I am showing here is actually related to a combinatoric problem. I can call it a puzzle, and I made a name for that. It's called restricted perfect shuffle. So for example, so I want to quickly go over this because I like this problem so much. So suppose you have a total of 12 items. Each item has a label, okay? And then, so at the beginning, suppose say you want to create 2 element groups. So we have a group containing element 1 and element 2, okay? And another group containing element 3 and element 4, and so on. So it's very easy to create such these groups, right? So that, there are no overlap, absolutely no overlap. And then we continue. Suppose say this is done. And then we want to create another set of groups. And this time we want to make sure that, say, in the previous round, I paired element 1 and element 2 together in one group. And here I want to make sure that Okay, I want to make sure there is no more, identical pairs. So I want to create a fair pairing in the next round and the next round. So, so this means that in the end, maybe there is a point that you cannot create any more pairings. So we ask first, if N is large, is it possible that we have an algorithm that can create this kind of non-overlapping pairing? Okay, this is one question. Another question is that when N is large, how many rounds can we go through? So, so this is just one of several, puzzle-like problems that I have been interested in. Thank you so much for your attention.
Welcome, everyone. My name is Andreas Stathopoulos. I work in high-performance scientific computing, and you'll get bored of my slides because it has no pictures. Sorry. But it has the names of my students, which I really treasure. One of them is right there. Yay, Heather is with us today. Jeremy and Luca are not with us, I think, today, and Yu Chen, I'm co-advising. Also, I have collaborators. High-performance scientific computing in general involves many areas. So I work basically with physicists. So Professor Ginos from physics department has been my longtime collaborator, and these are some of our postdocs who have found positions elsewhere. Okay. What the heck is this? What is scientific computing, right? Well, it's the study of numerical methods and techniques to efficiently solve computational problems in science and engineering. So there's many problems in science and engineering. You've seen some of my colleagues present their version of solutions to their problems. What I deal with is numerical methods, meaning mathematical solutions with the help of computers, right? And when we say numerical in computer science, we're not talking about real numbers that, 314159 that go on forever, right? We're talking about floating point numbers. And how do you deal with algorithms that have to deal with that? There's many applications and problems that require that. The tools that we've been using is numerical linear algebra. Numerical linear algebra is the combination of these floating point methods for linear algebra problems. But that's not all it, right? Because linear algebra can take you that far. At some points, you may need graph theory. You may need other algorithms, machine learning, not necessarily numerical. So this goes into play. And at the end of the day, you don't solve a problem unless you implement it somewhere and you have it running. So to do this for the big problems that we're discussing about in physics, chemistry, and other machine learning nowadays, we need high performance computing in there, okay? So numerical simulation, I deal with physics, but that's not all it, right? It starts from the matter, like what is matter made of? Okay, well, it's made of what, atoms? Not really. You go below. What is the electrons? No, not really. Go below. Quarks? Maybe. Go strings? I don't know. But at the end of the day, there's a lot of theory behind that, and there's numerical simulations that we need to solve to confirm the theory. How many people have heard of the Large Hadron Collider somewhere in middle of Europe that is going to blow a big black hole, and we all disappear yesterday, right? Well, that's what they're trying to solve, right? And in my research, actually, the lattice quantum, oops, is there a pointer here? Yay! So lattice quantum chromodynamics is what my collaborators are doing, and we are solving problems related to that. Of course, you start increasing the scale, and you see numerical mutations in molecules, biochemistry, brain science, material science, or you can go to structures, robotics, mechanical, civil engineer, or to earth, geology, for example, trying to solve weather prediction, climate prediction, yeah, that'd be nice, or astronomy, looking at that. So everywhere you see up there, we are talking about numerical methods. And of course, this is only to simulate. If you start talking about using and interpreting and understanding data, then we're going to the other section like machine learning, real-time data, image processing. All those guys underneath have numerical algorithms. Again, I've been mostly working on lattice quantum chromodynamics the last only 15 years. Before that, I was looking into material science. That was cool too. And now, who doesn't? I'm involved in machine learning as well. So I have collaborators in there. All right, so a little bit of quick, I have to show some math here, right? So what is numerical linear algebra? Well, we're trying to solve basic stuff, linear stuff, like linear systems of equations, AX equals B, nice. If A was a scalar, you know how to solve it, right? If it's a matrix, again, you have heard of how to solve it. But then if A is a matrix of a billion by billion size, what do you do? Okay, so my favorite is the second one, eigenvalue problems. This is what I've been working on. I've been putting out software for that. It's my life's work is eigenvalue problems. AX equals lambda x. It's the slight deviation from linearity if you want to go into NLA. Other things, matrix approximation, trace estimation. So some of you, these things are just names, right? For some more mathematically oriented, yes, oh yeah, I've heard of these things, right? But at the end of the day, all these are things that we need to compute to solve the problems for all those guys in the previous slide. Okay, my work has been focusing on iterative methods. Iterative methods, as opposed to, let's say, Gaussian elimination that you learned in elementary school, means what? You have an iteration that from step to step updates the solution slowly. And there's so many issues involved in that. And that's what I've been working on. The challenge, of course, is to have not only fast convergence, but robust convergence. Imagine a process that does not converge. I don't care how fast you do it, right? So robustness is important. Other algorithms, I did mention other algorithms, right? Like graph theory. We've been using that quite a bit. In fact, if you are to solve real world problems and not academic problems, you got to go outside the little boxes. We've been using graph theory quite a lot, especially coloring and partitioning. Recently, we've been going all out on Monte Carlo estimations, and you're asking, what the heck, why do you want to do that, right? Because the data is so large, we cannot do anything else. We have to do Monte Carlo. It's impossible otherwise to do that. But at the same time, you say, okay, I'm going to do Monte Carlo, close my eyes, you know, roll the dice, play on the casino and get the results out. But hey, we are scientists, right? At the end of the day, some optimization in the background would solve us. Would help us solve the problems much faster. So we've been dealing with various sort of global optimization methods, anywhere from classical Newton methods all the way to, I don't know what I'm doing, simulated annealing methods. And of course, the big kid in the block nowadays in my area is randomization. And I'm not talking about just quicksort, right? We all know quicksort, at least the computer scientists know about quicksort, the classical, the quintessential randomized algorithm. Now that randomization has becoming the major thing in NLA as well. It's amazing how well these things perform sometimes. So, the last bullet point that I mentioned there was high performance computing. So what do you need high performance computing for, and what do you need to do? We are talking, actually, no, we're not talking, we are handling matrices of 1 million to 1 billion size. This is a reality. Sometimes these guys are dense, the million size probably, and sometimes they're sparse, billion size. You cannot actually store a billion by billion size matrix, right? So these things don't even fit on a single core, and CPU, GPU, now forget it. You need to use parallel computing, right? You need to involve anywhere between, I don't know, a couple, like 2, 4, 5, or 10,000 nodes. Imagine a huge cluster or many clusters of 10,000 nodes, each one having, let's say, 40 or 60 cores working for you at the same time to solve these problems. We are talking about supercomputing type of infrastructure here. Some of our codes do work on some of the biggest supercomputers in the world. And of course, you see the hierarchy, right? You're talking about the nodes have to be many. Each one has to have many cores. And guess what? Each node may have also a couple of GPUs, FPGAs, field programming, gate arrays. This is crazy stuff. You can get a beautiful performance out of those if you know how to program them. All right. Again, my focus here has not been on producing new information on parallel computing rather than to get parallel computing to work for me. Some of the times we do produce new algorithms for parallel numerical algorithms, but don't consider that I work in architecture or any of these things. I just use all these things to solve numerical problems. Last but not least, I spent quite a bit of my time in software, producing software, not studying software, producing software has consumed him for more than 15 years now. So if you want to talk about any of these things, see me outside. Thank you.
All right. So this is, okay. Hello, everyone again. So this is, the time is 12:34. This means that we have just 11 minutes for the next 3 talks to complete, and then we're going to show you all that we are very agile. So the next 3 people, me included, just 11 minutes. That's all we got to be able to get to lunch. So I'm going to talk about and give an overview of my research, which is the main keywords: performance, reliability, and distributed systems. So systems are very large, very complicated, and they can have, how can we make them work better? That's the performance issue. How we can make them more reliable, making sure that they don't fail, making sure that they are safe and secure. All right, so what is performance? I'll start with that. Again, we're going to be talking again versus systems building versus prediction. It's actually before we build the system, it can be a great idea to predict it, so we make sure that we build the right thing. So that's the idea of prediction. And of course, we're using many ways to do that: stochastic models, machine learning. It's here as well. Actually, we see machine learning everywhere. All right, so I'm going to give like one simple example: machine learning inference. So I use this and I ask something to Siri. So what does Siri do? Siri does some natural language processing in the background, and typically there is some work that happens in the cloud, and then it goes to the actual serving aspect. And then we have like a very complicated system like this, right? So there is like batching of requests that go at the end on the cloud. That's this part over here. And then how can we do this thing efficiently? Actually, there is this yellow stuff that you can see on the slide: performance optimizer, queuing model. We profile what's going on. We use a lot of math. And at the end, we can just optimize this very complicated system. So that's an example of performance. Reliability: what if something fails? It should not be catastrophic. And then again, different ways to do things. We use data-driven approach, a lot of analysis, machine learning, and some applications. And now this is a great slide, which I have borrowed from the PhD defense of my former student, who's sitting over there at the audience. That's Lishan. She's a professor at George Mason University. And this actually illustrates what could happen, like bad things that would happen when just one single bit flips, right? And then there is like a little bit of algorithm here that shows that if I can have like even a bit flip happening, this could happen actually quite a bit on GPUs, just by, things like, temperature, voltage, cosmic rays. It happens all the time. This bit flip can be actually quite catastrophic. So we have examples and we have cases when these kinds of things can result in, especially in self-driving cars, in like really catching some corner cases that you would never actually trust the navigation of the self-driving car ever. All right, so that's an overview of what I'm doing. And the next speaker. I don't know how to do this. I don't know.
Okay. All right. My name is Advait Natrani, and I'm an assistant professor at William Mary, and I lead the Secure Platforms Lab. So I'm going to just tell you a little bit about what we do here in security research, right? Now, usually we hear about security when something breaks down, right? We hear about security generally in the media, whether it's, a botnet that's taken over millions of devices over the world, or whether it's a vulnerability in Android or iOS that essentially risks billions of users. And, like a couple of years ago, Equifax leaked half the country's SSN numbers. I don't know if you guys remember it. So we generally hear about things in the media, but have you ever asked yourself why? Why are we so bad at security? Well, the short answer is designing secure systems is hard. And that's for a very, very fundamental reason. It's because of this asymmetry between the attacker and the defender. When you take a look at this image, what do you see? You see a zip tie. Well, as an attacker, you get to exploit any one of these hundreds of zip ties in the system. As a defender, you need to find and root out every single one of these because that might unravel the security guarantees you're trying to provide. So the general problem is that the defender's job, just the system designer's job, is exceptionally difficult. And these zip ties, they're essentially metaphors for vulnerabilities, right? And the zip tie can exist at any stage. You can have a vulnerability in the operating system, in the cloud software that you use, in the applications that you use to interface between the cloud and your OS or the user, as well as in how people configure and use these systems. So if you really want to prevent vulnerabilities, if you really want to solve all of these problems, what we need is an approach that is essentially holistic and looks at the entire platform. And that's essentially what I work on. So I do work in platform security. It's about protecting everything by taking into account all of these components and their interactions. And that really leads to interesting questions where we use techniques as diverse as static analysis, from static analysis to software engineering technique like mutation testing, to modeling, to even user studies. So really the techniques aren't specific to one domain. And we essentially try to protect the user at all of these stages. So let me give you a couple of examples. So one of the most difficult things in building security systems is designing a system that is practical, right? The question is, how do you design a system that addresses a problem that's important now? How do you know what problems are important or relevant in the wild? Well, the short answer is, again, you can't unless you know exactly how people are trying to use the system, how people use the system. So we've tried to address this problem in the context of the smart home. Essentially, what we're doing is we're using a technique known as statistical language modeling. I'm sure you're aware of language modeling. This is just a more statistical variant of it. And the idea is that we are trying to predict home automation scenarios. That is essentially scenarios of how people use their home, how people automate their homes in a manner that's actually quite similar to how you do, how a predictive keyboard works, right? It looks at the previous words you've typed, and then it predicts the next word that it thinks you're most probably going to type. That's exactly how we're predicting future events in the home. And predicting these events, predicting these scenarios has helped us find vulnerabilities that other people could not have been able to find without knowing exactly how people use their homes, or executing these as test cases to evaluate security tools, and so on. So there are several use cases for this. I've also been working on evaluating security tools, because again, as security community really focuses on detecting vulnerabilities, we've built hundreds of tools over the years. But the real question is, are these tools even working? Are they effective? So we're trying to answer this using a technique known as mutation testing. I'm not going to go into details in the interest of time. But again, the general idea is we're testing the tools with as many difficult variants as we can. And we've actually been successful in identifying several flaws in several of these tools and very popular state-of-the-art tools that people just expect to work. Now, I want to spend some time talking about my lab. So I have 4 students. They should be somewhere in the crowd. One of my students recently graduated. Sunil, you'll see him in the student panel. And essentially, the focus of my lab is to make my students experts in one area that I'm not an expert in. Just like Dennis said in the morning, right? The students should be able to teach you something before they leave. So my students, as you see, work on very diverse topics within security, within platform security, and essentially have published in every single security venue that exists. All right. Now, in terms of lab culture, it's a really positive environment, a casual environment. A highlight of my lab is student-run lab meetings that I don't attend purposefully, because that allows students to, build a cohesive lab atmosphere together, right, to gel together and work on projects without me needing to even be there. So things just move around seamlessly without my presence. In terms of, so I'm always looking for students. In terms of what you need to know to be a student, there's not a specific set of skills I'm looking for, right? Like you saw, we work on a diverse set of things. You just need to be motivated, hardworking, and these are just the qualities that we relate to. So if you relate to these qualities, come talk to me during the breaks. Aside from that, finally, there's a significant focus on mentoring in my group. As a grad student, you can expect active mentoring from my side. You can also expect to have opportunities to mentor undergraduate students or junior grad students as you grow through the program, right? And this has actually been recognized at the university level as well. Finally, if you have any questions about any of these things, do meet me during lunch or any of the breaks or during the poster sessions. And that's it. Over to Dennis.
All right, so we just have a few minutes. I'll try to be as brief as I can. So I've picked one research thrust to talk about today that we are actively working in my lab. So does anybody know what this is? Do you know what GitHub Copilot is? Can you raise your hand if you know? Okay, almost everybody, but not everybody. So this is actually a pretty cool solution from Microsoft that uses large-scale neural language models to write the code for you, okay? And one cool fact is that Marty White, my former PhD student, was actually, as part of his dissertation, was very first to apply neural language models to autocomplete code. And since then it took off, and Microsoft bought GitHub and they've built Copilot. So that's basically in essence what we do. We try to harness powerful deep learning techniques to automate many software engineering tasks that developers do. But on the other hand, we also try to solve emerging problems, since we're building these systems that contain machine learning and deep learning components in them. We also need to figure out a way how to build these new systems and how to maintain them. And again, we've designed a number of solutions to support developers across software development lifecycle. So some of the problem highlights that we've addressed in the course of our research relate to designing model application UIs, auto-completing code, detecting code, supporting code reviews, so essentially checking the quality of code reviews, writing comments for the code reviews that you submit, automatically repairing programs, so finding bugs and automatically fixing the code that you might have, generating test asserts, again, generating mutants, helping with bug reporting and traceability link recovery. So one of the projects that we have in the lab right now, which is led by David, is actually related to the problem to understand what is happening inside of these very large-scale neural language models, right? So if you so one of the papers, actually, recent papers pointed out that these models are being used everywhere. One of the students who took my graduate class told me that he has friends in a startup who uses GitHub Copilot to write Android applications, okay? Some of my friends who are professors at Brown and a couple other universities complaining that they have trouble in introductory computer science classes because students are using Copilot to write assignments. And they really have to figure out what to do in that case, because they really want students to keep writing code, not just using these tools to write the code for them. But these models also do bad things, like generating code that may have security vulnerabilities in them, okay? So one big problem is how can we understand what is happening inside of these very large-scale models with billions of parameters, right? So David has been at the forefront of my lab to actually design techniques to not just drill down into these models and say, oh, you're trying to complete code, and the reason why you are making an error here is because in this layer or because of this weight, we're actually trying to explain it in terms of programming language concepts, okay? So like in this case, we're trying to complete this piece of code, and if it fails to do so, we'll try to tell you more details. Maybe the model was trained on the data and it's struggling with auto-completing blocks, so auto-completing operators, or maybe data types. And we use actual causal theory to do this analysis. Another big direction that we're interested in is actually trying to figure out how we're going to build these future systems containing machine learning in them. And this is software that everybody can write, or this is code that everybody can write. And this is basically part of existing or modern software systems out there. But more and more systems contain components that look like this. This is not source code. This is actually a neural network which has been trained on the data to do a particular task. But more and more components like this, you're going to find in these systems. And in fact, more and more quote, quote, code like this is going to be written by gradient descent, not you, okay? And this is actually going to change completely the way how we build and maintain these kind of systems. In fact, one recent study from Google have showed that they're building these really complicated systems that contain machine learning in them. However, most of that system is actual glue code, okay? Only 5% of that system is machine learning code. So there are lots and lots of challenges. We still have this dichotomy between developers who maintain all this infrastructure around the systems and developers who actually, design and train these models. So we do see that the paradigm shift is upon us in terms of how we build and maintain these kind of systems. So that is something that we're going to be actively looking in the very near future to figure major differences how software development practices are going to evolve. And of course, there are many challenges that need to be solved. And in particular, we are interested in maintenance and verification and validation challenges. Thank you very much. I think we are just right on time.
All right, guys, thank you so much. And let's go for lunch, right? We'll be back in 1 hour roughly. So yeah, enjoy and talk to people if you want, if you can.